Hi everyone. Today I would like to express my views on computational fluid dynamics in research perspective. Introduction of CFDs. Computational fluid dynamics plays an important role to investigate heat transfer and fluid flow situation by using numerical method. At present, CFD is one of the most important tool to design, analyze all type of turbomachinery. Turbomachine involve internal and external fluid flow problem in turbine and compressor. The main purpose of this work is to reduce the experimental cost and time. CFT is used by many industries in the development work to analyze, optimize and verify the performance of design. Some important research applications in CFTs are aerodynamics, power plant, turbomachinery, chemical process engineering, biomedical engineering. Let me discuss about turbomachinery, which is one of the example of computational fluid dynamic application. In growing population, fast developing technology and the development of living standard make a big challenge to find cheap and reliable energy. The energy which is harnessed from water is the widest among other natural resources. There are several ways to obtain energy from water, in which dam is one of the most efficient way of energy generation. Hydrokinetic method best way to obtain energy from water. Let's analyze flow inside rotating passage of turbo machine. A turbine is a rotary mechanical device that extracts energy from fluid flow and help for conveyance purpose. Moving fluid act on blade so that they move and impart rotational energy to rotor. Here I consider vertical turbine simulation for analysis. Let us see the geometry. This is vertical turbine with 3 blade geometry. Look at the view of the geometry. Bottom view, front view, right view of the geometry. Next geometry is spherical turbine geometry. This is for spherical turbine inside the pipe domain. Here we discuss boundary condition of the geometry. This is velocity inlet, pressure outlet, spherical turbine. Once the geometry process completed, next step move on to the meshing. The mesh consists of basic three-dimensional elements such as tetrahedron, hexahedron, quadrilateral pyramid and triangle prism. Hexahedron element has the highest accuracy of solution for the same number of cells on a given geometry, whereas other basic three-dimensional element has minimal amount of accuracy compared to the hexahedron, which is the reason why other basic three-dimensional elements are less considered while meshing process. Other basic three-dimensional elements are also considered the degenerate of the hexahedron element, where the edges of the considered hexahedron are reduced to 0 to form other basic three-dimensional element. Hence, the meshing is concentrated as hexahedron for the entire geometry. Hexahedron was used to discretize the fluid domain for the same cell count. Hexahedron will give more accurate solution, especially if the grid lines are aligned with the flow. The mesh density should be high enough to capture or elevated flow feature. The mesh adjustment to the wall should be fine enough to resolve the boundary layer flow. In boundary layer, quad, hexa and prism cell are prepared over triangle chest or pyramid. 3 measure of quality: skewness, smoothness, aspect ratio. Next mesh is prism layers. Here, mesh model is used to core volume is to generate orthogonal prismatic cell next to wall surface or boundaries. This layer of cell is necessary to improve the flow solution and provide a conformable mesh for the given flow model, which help in capturing the velocity across the boundary layer more accurately than depending on the standard wall function. The next method, computational methodology. Once the meshing process is completed, the next step is to set up physical behavior of fluid flow. The coupled flow solver is used to solve the Governing equation using K epsilon turbulence model. Rotating motion are enabled in a vertical turbine to estimate the torque. Look at the velocity profile. In this simulation, turbine should be placed in a rectangular box. This is velocity inlet portion, pressure outlet portion. Here we are enabled rotating motion with 1000 rpm. Look at the pressure profile. High pressure is created at this point due to water flow in turbine blade. Look at the blade pressure profile. This simulation be extended to find the turbine performance by changing the blade profile as well as helix angle at different free stream velocity. The present study is simulated for 3 blade turbine. Further, a correlation is developed for prediction of reduction in torque and power coefficient for torque with solidity ratio. The same computational methodology is also followed by the spherical turbine simulation. Look at the velocity profile. This is velocity inlet portion, pressure outlet portion, spherical turbine blade profile. Look at the pressure profile, blade pressure profile. Let us see the video. In this animation, we are going to analyze the torque of the turbine blade. It is varying by velocity and speed. The investigation undertaken can further be extended to find the turbine performance by changing the blade profile as well as the helix angle at different free stream velocity. Thank you.